All right, good afternoon, everyone. How did your homework go? Did you guys go through your homework? And if you have any questions, please go ahead and ask. Okay, any questions from the book or the problems that I put on Brightspace? All right, so let me ask you questions before we start with the B from the given questions. All right, so we will do that. And my question is, I have A, B, and A, B, and X are n by n matrices. And I gave you an equation. The goal of this equation is to learn how to solve for a matrix and how to use the properties of the inverse times B squared A inverse. And the question is solve for X. So all of them are matrices. And the question is solve for the matrix X in terms of A, B. So solve for X in terms of A and B. Okay, so how shall I do that? Anybody has any idea? Anybody who tried it can have any idea how would I do that? Did anybody try to do this problem? Okay, so you have to solve. So you have the X in here. And I have to solve it. Somehow I need to get this X outside this idea, this parenthesis. Okay, I'll give you 2 minutes and get going. 2 minutes to scratch something in front of you, and then you guys have to share with me what you did. So 2 minutes, I'm starting right now. All right, who's ready? So who's ready to share their solution with us? Please get going. Anyone? You guys were supposed to have thought about this. Go on.
So you take both sides. So you take the inverse on both sides of the equation, and you rewrite A inverse X, the inverse of A inverse times X, and you rewrite that as X inverse times A. Then on the other side.
Wait. I have to follow you. You take the inverse from both sides, correct? Is this what you told me?
Well, actually, I just took the inverse of A inverse X and rewrote it as X inverse.
Okay, so you worked with this one.
Yes.
All right, so I'm going to take another piece of paper and I'll do verbatim what you said because I don't want to put words in your mouth. Okay, so my understanding, what did you write here? Please get going.
Okay, x inverse times a equals a times parentheses a inverse times b inverse times b inverse.
Absolutely correct. Okay, because
And,
b squared, yes, because b squared a is b times b times b. So when you take its inverse, we go backward. It's a inverse, b inverse, b inverse. Absolutely correct. Keep going, please.
And then on the right side of the equal sign, I took the parentheses and shifted them over such that it's parentheses a times a inverse times b inverse parentheses b inverse on the outside, and the a times a inverse turned into the identity, and that left just b inverse times b inverse on the right side.
Very good. I'm following you verbatim. Proceed.
Okay. Yeah. And then I left multiplied both sides by just x. And
So left
on the left
multiplied by
side,
x.
yeah, both sides of left multiplied by x. And that's right. And the x times x inverse became the identity again, which left just a on the left side. And the right side became that, yes. Then I took the inverse, that I right multiplied both sides by the inverse of b inverse times b inverse, what was in the parentheses there.
Now I lost you. Right multiply by what?
I took b inverse times b inverse, and I put parentheses around them, and I multiplied both sides by the inverse of that. And
I'm still losing you. I don't know what you did here. If anybody understood, let me know.
I took the inverse of that, what's under the
what do you want me to write here?
B inverse times B inverse.
I have it.
Well, I took the inverse of I took the inverse of that. Well, what you're pointing at?
How can you take the inverse? It is the inverse. I still having trouble.
I think what he's trying to do is like what you would do in an algebra is divide B.
No, I'm not trying to divide.
No division. That was very clear.
No.
We do not divide by.
I'm not doing division.
I'm not saying no. I'm just comparing. Like if he was doing regular algebra, then he would divide. So I think he's multiplying by the inverse on both sides, right?
So I'm still not following what you want me to do at this stage. Just trying to get it to the other. Yeah, you're trying to get this to the other side, right?
I'm trying to isolate x. That's what I'm trying to do.
Yeah. So right multiply by. How can you get rid of B inverse?
By you take the inverse of an inverse.
Which
Anytime
is?
you take parentheses.
What's the inverse of B inverse?
B, just
B.
Yeah, that's what I was trying to say.
Yeah, so this is gonna give me A
so
times B times the identity, multiply again by, right multiply by B. It's gonna give me A, B times B is X, B inverse identity B, but this again will give me the identity, and now we're isolating your X, okay. End of the problem.
That's what I was trying to say.
Yeah,
that's what I got.
Yeah, so right multiply by B. Okay, so that's absolutely one way to do this problem. Every piece he did it very well. He used all the property of the inverse correctly, and we were able to do that. All right. So Another way you could have done this, that's absolutely fine, correct. Another way, if you want, you could have done it like this. That's what I understood at the beginning. The inverse of that is equal to this. So we take the inverse from both sides. I said if those are equal, their inverse will have to be equal because they are the same thing. But now the inverse of the inverse will give me this. So that's another way to do it, equal. Now the inverse of that would be b squared a inverse times a inverse. So we have to go, oh, sorry, I missed something. Okay, my apology. So this is gonna give me a inverse x equal b squared a inverse times a inverse. So that's another approach you can do it, which will give me a inverse x equal b squared, because those two will give me the identity. Now left multiply by a, and will give me a inverse x is ab squared, or x equal a times b squared. All right, and that's the other approach you can do. Right? So as I said, the goal here is really to practice our algebra. And sometimes if you want to solve for a matrix, you know what, if we learn how to solve for a matrix if we have an equation. Right? Okay, so now we move on to section 2.3, which is what we call, any questions before I move on? All right. Section 2.3 is called the invertible metric theorem. So section 2.3, okay? And we've seen a lot of the theorem, and it's really rely on the worksheet I started last time. So I'm gonna go back a little bit to it, and I ask you questions along, and then we state the theorem together. That's usually how I state the theorem. Usually the student can tell me the theorem by themselves. So a little bit, I go back to last week's worksheet. So I will write what I'm talking about. So we had the matrix A, and I kept it in front of me so I don't lose track of it. Sorry, give me a second. Okay, here it is. So we had the matrix A, 1, 1, 0, minus 1, 0, 1, 0, 0, 1. That was my matrix. And my first question is show that A invertible. So show A invertible and find A inverse. Of course, we're not going to repeat the word, but let's see how the idea, how to show that A invertible. We start with the matrix A together with the identity, this huge matrix. And we solved. And the idea is, if you can get to the identity from here to here, then the algorithm tell you your matrix is invertible. And that's exactly what we did. We did all this, and then we were able to get here. So this matrix is invertible, and we got some stuff in here. So that's the inverse. 1, 1, minus 1, 0, 0, 1. So being able to get to the identity will allow me to find the inverse immediately. Now, questions we asked last time, some of the questions, not all of them, some of the questions. If I focus a little bit on the columns of A, A1, A2, and A3, right? What can we say about the columns of A in the following sense? Independent or dependent? Okay, so are the columns of A, so this matrix is invertible. And the reason it's invertible, it is because it is row reduced to the identity. So this will allow me basically to algorithmically to construct the inverse. Now the vectors A1, A2 are linearly what? Quickly. Dependent or independent? I want answers on chat very quick. Independent or dependent? Absolutely independent. Okay, the columns. And let us a little bit remember why. Because if I try to solve this equation, I try to solve it equal to 0. And the question is, do I have a non-zero solution? So let us remember how we do that. I put the 0 vector here. I put A1, A2, A3. It means basically I'm putting the matrix A here and the 0 vector. But we know what happened to A. We know that A at the end is going to take me to the identity. We know that about A. We've already done it. It means the solutions has to be, I have a pivot, I have a pivot, I have a pivot. The solution has to be the 0 solution. My vectors are independent, right? Question number 2. Okay, I'll take another piece of paper because I'm always going to be referring to the same matrix, Question number 2 is the following. If B is any vector in R3, so be a vector in R3, something with 3 components, okay? And I'm trying to solve the system AX equal to B. So I'm not giving you B, any B. And my question, the system AX equal to B, is it consistent or non-consistent for some B? Or is it consistent for all B? Or for some B it is, and for some others it's not? What can we say about the system AX equal to B? Is it consistent for all B? Yes or not? And why? Of course, because you have to understand the picture. Is it consistent for all B? What's your hunch? And then why? Anybody? Yes. So, okay, consistent for all B. And now let us see why, because you have to understand this once and for all. Because if I try to solve this, I don't know what B is. I know A. 1, 1, 0, minus 1, 0, 1, 0, 0, 1. B is, I don't know what it is. That's my A. Now, am I going to have a solution? It means, is there a way I can have inconsistency? And the answer, no. Because if I take my A and I start reducing, this is going to go here. And the B's, I don't know what will happen to them. Okay, now if we look at this system, every row have a leading. So I have a leading in every row. So here we have a leading. A has a leading in every row. Why will the leading in every row? A, the coefficient matrix. So what does this mean? It means the system is consistent because the scenario, the following scenario, 0, 0, 0, non-zero can't occur. There is no way I can have this scenario. Why? Because I have a pivot in every row, not column. I have a pivot in this row, in here and here. So I cannot have 0, 0, non-zero for the augmented, because every one of the rows has a leading. So this scenario cannot occur. It means I always have consistency. So no matter what I put here, I'm going to have a solution. And this is really all tied down to the fact that this matrix A was actually equivalent to the identity, which also caused the invertibility of the matrix. All right, my last question is the following before we state the theorem. If I take all possible linear combination of my column vector, all possible linear combination, means I start combining them. And the question is this equal to R3? Means if I take every possible, it means, is every vector in R3? I'm really asking the same question in different this case. Every vector in R3, a linear combination of A1, A2, and A3. What do you think? Yes or no? And then I justify myself. Is if I pick an arbitrary vector in here, can I always find weight so that this vector could be a combination of those? Okay, so I'm getting some yeses, and the answer is absolutely yes. Again, why? Because if I take any vector B, whose B is any vector, and the question is, can we find x1, x2, x3, such that if I take the linear combination with those weights, I reach the vector B? Okay, but this is equivalent to solve the following system. A1, A2, A3B. That's really equivalent to solve the system. And the system is consistent. We know that. Consistent. So any vector I want, I can write as a combination of those three vectors. Okay. So the invertibility of the matrix, or the fact that the matrix A is equivalent to the identity, will really put a lot of ideas together. And now we're going to state a theorem that we call the invertible matrix theorem. And the theorem actually combines almost every concept we've seen so far. So slowly, I will state it. So the invertible matrix theorem. Matrix theorem. And some, if you go online, it's usually called linear algebra in a nutshell. They like to give it this name, linear algebra in a nutshell. All right, so don't worry about that. So this is the theorem. Suppose A n by n matrix. And A has columns, A1. So I'm going to emphasize the columns and the system, and AN. Those are the columns of A. Like in the previous one I gave you, it was A with 3 columns, A1, A2, and A3. Then the following are equivalent. Now, what does this mean? The following are equivalent. So I'm going to give you a bunch of statements are equivalent. What does this mean? It means I'm going to give you a bunch of statements. They are equivalent. It means if one is true, means if one of the statement is true, if one is true, the rest are also true. Okay, so let us go through those statements verbatim. Okay. A invertible. So suppose A is invertible. It means we can find, that's what invertibility means. We can find C such that AC equals CA equal to identity. Now I start asking you questions. If this is the case, what can we say about the system AX equal to 0? If A is invertible, what can we say about the system AX equal to 0? What does the invertibility of the matrix tells me about that? That's a homogeneous system. It's absolutely consistent because 0 is a solution. What else can we say about it? No, not yet. This is a system. We don't talk about independent system. We talk about independent vectors. System, it means we talk about their solution. What can we say about the solution of the system X equal to 0? How many has a unique solution? Namely, X equal to 0. Okay, because once the matrix has an inverse, means there is something that will give me the identity, then if I try to solve AX equal to 0, as we did several times, we can multiply by A inverse. And multiplying by A inverse will help me to capture my X back. which gonna give me the 0 vector. So the invertibility, it means the existence of something. When you multiply it by A, give you the identity, force X equal to 0 to have a unique solution. Now see, so if you have X equal to 0, have a unique solution. What can we say about the reduced echelon form of A? What can we say about it? So this is my A. Always imagine the picture. This is my A. When I solve, I get one solution. It means I need to have a pivot. The unique solution, it means there is a pivot in every row. It is the identity. Okay, we keep going. How many leading entry A will have? So the how many pivot or how many leading entry? It means when we reduce it, so how many pivot, it means when you reduce the matrix, how many leading you get. It means A has n leading or n pivot. All right, A, B, C, D, E. Very good. What can we say about the system AX equal to B? That's a system. What can we say? So whenever I say system, it means, okay, we're talking about consistency. That's what I say about system. What can we say about the system AX equal to B? It is consistent for all B. No matter what B is, we have consistency. No matter what I throw at you, if A is invertible, we can solve the system. Now, the last two pieces, so A, B, C, D, E, F, are about the columns of A. So, you know, A matrix have columns. What can we say about the columns of A? First, if A is invertible, the columns are linearly independent. Okay, so if the matrix is invertible, the columns have to be linearly independent. It's always the same picture. The invertibility forces the echelon form to be the identity. If the echelon form the identity, the columns will have to be linearly independent. And the last piece of the theorem tells me that if I take all linear combination of the columns, so these are n, let me emphasize, now the columns of A are n vectors in Rn. So it means we have n vectors, and each vector, the dimension of it is n. Then the span of it is everything. It means that any vector in Rn could be written is a linear combination of A1 through AN. Okay, so this is what we call the invertible matrix theorem. It's actually connect every idea that we have. So if the column of a matrix R, if a matrix is invertible, it means that we can find something. We multiply it by, we get the identity, then all those will hold. Now, the following are equivalent means that. Means if I pick any properties, suppose I pick this one. If the columns are linearly independent, then all the rest will have to hold. So the following are equivalent means if any of them is true, the rest are true. Means that if you know that the columns are linearly independent, everything will follow. And basically the idea is that suppose I assume linearly independent, why everything follow? Because if they are linearly independent, so if I take A1 through AN, I'm going to have a pivot in every column. Having a pivot in every column means I have n pivot. If I have n leading, it means my echelon form is going to be the identity. So I can invert it. And also the span will be Rn, because if they are linearly independent and I have n vector in Rn, then every row will have to have a leading. So we can always solve for the weight. There is no issue with the weight. So that's what we call the invertible matrix theorem. It actually puts together every idea we've learned, but it works only, of course, when the matrix A is n by n, not less than that. So now let me ask you, when I move a paper, please let me know if it's okay or not. Okay, so let me ask you now very straightforward questions just so that we can interact with the theorem a little bit. I'm going to give you 3 matrices. And my question to you is, just by looking at them, usually we cannot by looking at them, but those are simple. Just by looking at them, tell me if the matrix is invertible or not, and which section of the invertible matrix theorem allows you to do that. So I say this matrix, is it invertible, yes or no? And you have to justify your answer just by looking at it. Invertible, yes, not, justify. Okay. You guys can unmute yourself if you like to speak or write in chat, whatever you're comfortable with. So do you think I can invert this matrix?
I would say yes, but I can't really explain why. It just looks like it's pretty simple. I mean, you got a leading in every column.
That's the crucial idea. I have a leading. I have a leading in every column. So can I reduce this to the identity, you think?
Yes.
If I have a leading, can I reduce it? Very easily. This I can make into 1 of the back because I can divide by 15. I have my 1 here. I can make this into zeros. I can make this into zeros. Okay, so this is immediately an invertible matrix. And actually, if I solve the system 0, 0, 0, think about it this way. How many solutions I'm going to have? 15 x3 is 0. x3 will be 0. x2 will be 0. x1 equals 0. So this is absolutely invertible because I have a pivot in every column. So invertible because we have a pivot in the 3 pivot. That's a 3 by 3 matrix with 3 pivots. So because we have 3 pivots. So you can go from here to the identity. So you can construct your inverse of the back immediately. All right, so by looking at this, we know it's invertible because we have those pivots. So solving 0, 0, 0, I'm going to get a unique solution, and so on and so forth. Now, immediately 2. Do you think this is invertible?
Immediately, no.
Immediately, no. Not invertible because how many pivots this will have? That's it. These are the only 2 pivots we have. So if I solve ax equal to 0, of course, I cannot solve it at this stage. I have to go one more step, and this step will make this into a 0. I'm going to have a free variable in x3. The solution will not be unique. The columns are not linearly independent. You name it, not invertible because we only have 2 pivots. Okay, so we need 3 pivots so we can go to the identity. Otherwise, it doesn't work. Okay, example number 3. Sorry, I had a mistake here. I don't want 1, my apology. 5. All right. Again, I want you to look at it very carefully. And my question is, invertible, not invertible?
Not.
If you say not, you justify. If you say yes, you justify.
Not because they're the same. The second row and the third row, they're the same.
The second row?
You could divide by 3 there.
Which one?
The third row, divide by 3, get 1. Sorry, hold on, I'm thinking now. My bad.
That's okay. Anybody else? Okay, not invertible because. You have to give me an answer. I mean, just by looking at it in a way. Usually I'm not giving them hard. I'll give them so that you guys can look at them.
Because they're linearly dependent.
They are linearly dependent because. Which one are dependent? I want to look at this vector and this vector. What do you notice? How did I pick A2? A2 times 2 times 2. A2 is 2A1. So because the columns are linearly dependent. So when I reduce, there is no way I'm going to get the identity because the columns are linearly dependent. That immediately will stop the invertibility. So if you guys take this matrix and reduce it, what you're going to get is something along this line. You will not get, you're going to get something like that. If you reduce it, you will get something like this. That will be the reduction of this matrix. And this is caused by the fact that those are linearly dependent. All right, so whenever you have a matrix and you just look at it and realize that one is a scalar multiple of is this combination of the other, immediately there is no way you will be able to find a matrix. When you multiply it by, you get the identity. Okay. All right, question number 4. So I did a lot in R3. Everything I did in R3 can go to R4. So suppose the vectors are irrelevant. I just write a bunch of numbers. So I have a matrix A. I am in R4. So this is my A1, A2, A3, A4. And then I reduce it. And I get the identity. And my question to you is that, do the columns of A span R4? It means if I take all possible linear combination, do I get everything in R4?
Immediately, yes.
Immediately, yes, because
of G on the invertible matrix theorem.
Because of the invertible matrix theorem. Or another reason, if you want to think about it, if I pick any vector here, B1, B2, B3, B4, any vector, at time I ask myself, can I find a weight so that I put on the vectors and I get this? But we know that this is really equivalent to solve the system. Can the system be inconsistent? No way, because I have a pivot in every row. So there is no 0, 0, 0, 0 non-zero because I have a pivot here in every row. So the span equal R4, or as you said, because 4 linearly independent vectors in R4 span R4. Now, how about those vectors? This is my A, and I reduce it. This is A1, A2, A3. I get that. Question number 1. So now I have 3 vectors. 3 vectors now. So I am really in a different universe. 3 vectors in R4. Question number 1, are the vectors linearly independent? Yes or no? Okay. Somebody tell me yes, because if we solve the system, 0, 0, 0, 0, 0, 0, 0, I have a leading in every column. So the x3 will be 0, x2 0, x1 0, linearly independent. Okay, now is the span equal to R4? Means can I get every vector in R4 as a combination of those 3 vectors? And intuitively, what's gonna get in the way? Algebraically, actually. So can I write any vector here as a combination? What do you think? If I plop any vector here, any vector, can I always find weight so that this vector is a combination of A1, A2, and A3? What would be your, what do you think? So can I write any one as a combination of those? Okay, and the idea is no, not necessarily, because when I reduce, I don't have a pivot, a leading in every row. So when I reduce, I may very well have this scenario, and I will have this scenario. So I can have a scenario where when this is reduced, I will have 0, 0, 0, non-zero, causing inconsistency in the system. So 3 vectors in R3, even if they are linearly independent, they do not span R4. Even they are linearly independent, they definitely do not span R4. I need them to be linearly independent. I need to be able to have this pivot in every row so I can solve for every other vector. All right. So these are some conclusions we get from that. All right. Okay, not today, after this section, we're gonna move to, so that's the idea of the invertible matrix, the importance of it. It combines a lot of ideas of the course, and they work only when A is n by n. So that's really our commitment to that chapter. All right. Today, we're gonna move back to basically chapter 1, and there are 2 sections that I skipped in this in chapter 1, not because they are not important, just because I don't think you were comfortable enough to do that material. So I'm gonna go back to section 1.8, I think. And it's called Introduction to Linear Transformation. Okay, Introduction to Linear Transformation. Now, before we start talking about this, we're going to talk about functions a little bit, because transformation is a fancy word for function, no more, no less. So what is a function? Let's go back a little bit to calculus and pre-calculus. A function is a rule. Is a rule. Give it an input, and this rule will spit out an output for you. Okay, that's what a function is. Now, in calculus 1, calculus 2, and pre-calculus, most of your function took for input a real number and spits out a real number. So the input was a number, the output was a number. So we talked about f of x equal x squared. The input is a number, 1, 2, 3. The output is a number. All right. Now, in calculus 3, the picture changed a little bit, right? In calculus 3, what did you take for input? Not one number. In calculus 3, you start thinking about functions with 2 variables. So your input became, basically for me, it's a vector in R2. That's really what your input is, because for me, R2 is nothing more than the collection of all a pair of numbers, ordered pair of numbers. So whether you write it this way or write it that way, this is for me in R2. So but in calculus 3, you took for input 2 numbers and your output is a real number. So you talked about f of xy equal to x squared plus y. That was a function. Right now we say, okay, why don't we generalize a little bit more? So now what we're gonna look at function where the input is in R2, it means ordered pair. In R3, it means 3 pairs of numbers, a list of 3 numbers, or in R4. So we're gonna start taking for input something not necessarily in R1 or R2 or R3, that's gonna be the input. And the output itself is not only a real number anymore, the output is also a vector. So the transformation is going to be like a function, it's a rule, where the input is a vector in R2, R3, R4, and the output is also a vector, okay? So in this case, and we have a notation we're going to introduce. If you are in calculus 1, for me, the function is, we're going to say it's from R to R in general. Means a specific, it means the input is real, the output is real. In calculus 2, we're gonna say it's from R2 to R. Your input is an ordered pair, the output is a number. Now, we're gonna say it is from Rn to Rm. It means my function has for input a vector in R1, R2, R3, R14, and the output is also a vector in Rm. And we're gonna call those transformation instead of calling them functions. Okay, so which is the same thing. All right, so what's a transformation in linear algebra? So a transformation is nothing more than a function, no more, no less. So transformation, definition. a transformation T, so as I said, it means a function, it means a rule. You give it an input, it gives you an output. A transformation is a function or a rule. That's what a function is. But it takes its input from Rn to Rm. Okay, so the input is a vector in Rn, the output is a vector for Rm. So when I see transformation, I basically two spaces. One is Rn and one is Rm. That's what I see. There is a 0 in each one of them. And T is something that it takes a vector here and associate to it a vector right there. So that's really the picture. So it's a little bit more general than what you have seen so far. So T, now how do we write this? So we write, that's the notation we use. T from Rn, arrow Rm. That's how we will be writing. And it takes X, vector X, and associate to it something called T of X. So this is my X here, and my function will take it to T of X. That's Rn is called the domain. Okay, so that's the domain. So our transformation will have output for every X in Rn, and where the function takes its value, we call it the codomain. Is where the values are. That's the codomain. Now, a little bit of terminology that it's used in the book and it's used in every math book usually. If X is in Rn, T of X, which it means the output vector, is sometimes called, and you have to get used to that, the image of X under T. So the output vector, we give it a name sometimes, and instead of calling it T of X, we give it the name, it's the image of X under T. So it's nothing more than a sophisticated word for the output vector, no more, no less. 2, another word, the idea of a range. Let me take you back to calculus 1 before I define it. Suppose I have the function f of x equal x squared. Of x equal x squared, which is the very basic simple function, right? And I tell you, is -1 in the range of f? Do you guys remember what does it mean, the range of f? Anybody has a recollection? What's the range of a function? The y values. Yeah, the range are all the output values. All the output values. So if I tell you, is -1 in the range? No, because there is no input that takes you to -1. Now, is 2 in the range? Yes, because I can find, let me take something easier. Is 4 in the range? Yes, 4 in the range because I can find 2x values that are mapped into 4. So 4 in the range because I can give you 2 values of x which are mapped into 4. We're going to define the same definition here. So suppose I have a vector b. We say that b, a vector b. So I start with a vector b in Rm. These are just a bunch of definitions for now. We say that b in the range of t, in the range of t, if b is an output value. What does it mean? If we can find x, we can find a value x in Rn such that t maps x into b. Okay, so let b be a vector in Rn. We say that b in the range if it is an output value. It means if there is an input that's mapped into it. Okay, now let us take 2 simple examples to understand all those the vocabulary, and then we work with them. So first let us Let's take the first simple example just to understand how we write this. So example 1, suppose I take the following function, f of t of x equal, let me take t from R2 to R3. Okay, wait. All right. Are you done? Okay, sure. Please let me know because I'm not watching you. So suppose t is from R2 to R3. So this is my domain. So I'm taking a vector in here and I'm mapping it to a vector in R3. Okay, now what's the rule here? This is the following rule. T takes x1, x2 to the following. So this is, so I went from R1 to R2. It means I have to take a vector in R2 to a vector in R3. So I need 3 things here. So I'm gonna write them. X2, I don't know, for x2 plus 6. Okay. So this is just to understand what this means. So suppose I tell you find the image of the vector 1, 2 of u equal 1, 2 under t. Okay? It's just too complicated of a sentence, but you have to know it because the book uses it. So find the image of u under t. This means as simple as that. This means find t of 1, 2. It means this transformation that I gave you a rule will take the vector 1, 2 somewhere. Where does it take it? All right, let us understand how we read that. So 1, 2 is equal to what? So this is a vector 1, 2. Okay, and my function takes it somewhere. Where does it take it? All right, let us use the rule verbatim. What does this rule do? Takes the first component, square it, and add to it 2 times the second component. As simple as that. x2 is the second component, and the third one is 4 times the second component plus 6. That's how we read it. All right, so this is going to give me simple 1 plus 4, that's a 5, that's a 2, and this gives me 14. Means you have to think that you have a function that takes 1, 2 to the vector 5, 2, 14, somewhere in here. So that's the vector taken to that. Okay, so that's really an example of how a transformation will be given. Now, the type of transformation we'll be interested in, honestly, will not be that. We're going to be interested in a very specific type of functions. So let me talk about that. When you first learn functions, the function that you guys learn are something like that. F of x equal 2 times x, the simplest function. F of x equal 3 times x. Okay, that's really the most basic function we use. And then probably you learn the exponential function, you become, okay? So those functions have names. This one is called exponential function. This one is kind of a linear function. Okay. In this class, we're going to study a specific type of function and the function which are generated using a matrix. So very specific type of function. We're not going to study all type of transformation, very specific one. We're going to study something called matrix transformation. So what's a matrix transformation? Okay, matrix transformation. So we're going to use matrices to define functions, matrix transformation. So what do we mean? So when I use the word matrix transformation, what I am talking, what type of transformation I have in mind. Okay, the following. So let A be a n by n matrix. So it's not anymore n by n, we're back to the old scenario. And let T be the transformation from, okay, I will fill this in a minute because you have to help me out. This given by. All right, so that's what given by T of X equal A times X. So suppose A is the n by n matrix and T the transformation from R to R given by A times X. For this to make sense, what should be the number here? What should be the number here? So we're going to use matrices to construct functions. If A is n by n, if you ever forget, this vector x, of course that's a vector, so we have one column, will have to be n by 1. It means this has to go from Rn, and when I multiply them, I'm going to have n by 1 to Rn. Okay, so what's a matrix transformation? It's like when I tell you in calculus an exponential, you think about this rule, 2 to the x, 3 to the x, 4 to the x. In this class, when I'm talking about matrix, you have to think about the following, that you're starting with a matrix A, and your transformation takes a vector x to A times x. This type of transformation, which is obtained by this rule, are called matrix transformation. And those are the ones that we will be working with in those two sections. So let us take two examples of matrix transformation. Example number 1, which really relate to start taking us back to what we've been doing all the time. So let's see example number 1. So let me take the matrix A to be equal to the following. 1, 3, minus 1, and 2, 3, 1. Let A be the matrix. And T, the transformation from here to here, that in a minute we decide, given by, so that's the following matrix transformation. It takes the vector x to A times x. So I set up as a matrix, and now I'm going to define the linear transformation that takes x to A times x. Now, before I put the stuff, what should be the number here? Because this transformation should make sense to us. What should I put here? What should I put here? So you guys know what to put if you're faced with this problem. Anybody? What should go here? But I want this to make sense. My vector x should be where? I want this to make sense. My matrix A is 3 by 2. For this to make sense, my vector x has to be 2 by 1. It means my vector x has to be in R2, and this has to be R3. So this is my transformation now. So I'm taking a function from R2 into R3. That's my transformation. Okay? And that's a matrix transformation because the rule is A times X. That's what we call matrix. If I give you a transformation, I tell you it's given by A times X, that's what we call a matrix transformation. It means obtained by this type of rule. Now let me ask now 2 questions just to again understand the picture a little bit. I mean, understand the definition actually, not even the picture now, only the definition. So question number 1, find the image of any vectors. So find the image of the vector 2, 3 under T. It means, as I said before, it means find T of 2, 3. Okay, that's my first question. It means this matrix, we have a vector here, it takes it somewhere. Where does it take it? So let's see what the rule are. What does T do to a vector? What's the rule? What T does is takes the matrix A and times it by the vector. That's what the rule is. Now my matrix A, I gave it to you. So we're gonna write it down. 1, 3, minus 1, 2, 3, 1. So this is my matrix A times the vector 2, 3. And I should get a vector in R3 because the product will give me a vector in R3. So T will take the vector where? So we're gonna compute here, 2 row vector, 2 plus, what was this? That's an 8. And that's gonna give me 6 plus 9, that's a 15. And it'll give me minus 2 plus 3, minus 2 plus 3, it gives me 1. It means my matrix will take, the vector 2, 3 to the vector somewhere here, 8, 9, 15. Okay. Now let us a little bit understand the word range. What does the range mean? So I'm gonna work the same problem, but now I'm gonna introduce the word range to understand that word. So this is A. Range, it means output vector. So now I'm gonna take an output vector. It means I'm gonna take a vector in here. I'm gonna ask you, can you find something in R2 that's mapped into it? So let me pick a vector B. Suppose I take a vector, I have a vector here, 1, 0, 2. That's my vector. And I'm gonna ask you, is the vector in the range? What does this mean? It means, can you find something somewhere here that when you let T act on it, it goes to 1, 2, 3. So that's what I'm after. Is there something here that takes me to 1, 0, 2? That's what it means in the range. So question number 2 is, let B be the following vector. Equal 1, 0, 2. And the question is B in the range of T? Just basically the language of function, we are a little bit trying to generalize it. That's really what we are doing, at least for today. So is B in the range of T? What does this mean? It means, can we find, that's what it means. Can we find a vector X in R2? Can we find an input vector such that T of X equal to B? That's really what it means. It means, can you give me something here that under T, it will go right there? All right, but now, how do we ask ourselves? It means, can we find X such that? What does T do? What's the rule for T? Such that A times X equal to B. So back to an old scenario. Can I find a vector such that A times it? Because that's the rule of my transformation. All right, now it means I need to find a vector such that if I take A, my A was 1, 3, minus 1, 2, 3, 1, and I multiply it by my vector. My vector is an input vector, that's X1. Can I find, let's say this gives me 1, 0, 2. So that's really equivalent to solve that. Now, can we solve this? Now, of course, now we are in familiar territory, very familiar. So I'm solving a system, x1 plus 2x2 equal to 1. But now the solution is actually an input vector. That's what the solution is. So I will have 1, 2, 1, 3, 3, 0, minus 1, 1, and 2. So it's really boiling down to solve the system. All right. So we should know how to solve this. And what should we get? So if I didn't do a stupid mistake, this gave me 1, 2, 1. And it gave me a 0, 1, 1. And it gave me 0, 0, 0. Okay, so it means obviously the system is consistent. And this will give me that x2 is 1. X1 is 1 minus 2x2, which is equal to minus 1. It means my vector B is in the range, is an output value. B in the range. And in the range, and it's the image of which vector, and T of minus 1, 1 will give me the vector B. That's really what it means to be in the range. It means, you know, can you find something which is mapped into it? So that's the idea of the range. Right. The last 10 minutes we have, I would like to give life a little bit to those transformations. So let me give you example of matrices, and we're gonna a little bit try to understand them geometrically. We won't be able to understand every transformation geometrically, but some of them we can, and that's the examples I will give right now. So some geometric matrix transformation, just to give life to this idea. So some geometric matrix transformation. Okay, some geometric one. So I'm going to take the following matrix. Let A be the matrix 2, 0, 0, 2. Okay, and my goal is actually understand when this matrix acts on a vector, what does this matrix actually do to a vector? So the question is, let T be the matrix transformation from R2, because it has to be R2, the output will be in R2, that take X to A times X. So that's my matrix transformation that corresponds to this matrix A. Okay, so this is R2, and I'm going, for this particular example, I'm going to sketch the input. Since the input and output are vectors in R2, I'm going to sketch them actually on the same R2, because as you will see in a second, is actually interesting. So what does T do to a vector? Let us compute. If I take any vector x1, x2, what does this transformation, this matrix transformation do? So it takes the vector matrix A and times it with x1, x2. Okay, but this is going to be equal to what? Let us multiply them. Row, column, 2 x1 plus 0 to x2. Okay, so back to you now. This is my vector x1, x2. What does this transformation do to this vector? Geometrically. I want you to look at it for a little bit and tell me geometrically, this matrix transformation obtained by this matrix does what to a vector? This is my vector x right here. What does A do to it? I want you to look at it carefully. You don't need too much time. Just think about it. What is the output vector here? Scale the vector. Yeah, because if you look carefully, this is what? This is 2 times x1, x2. So what this vector, this matrix does, it actually takes a vector and stretch it by a factor of 2. This particular matrix, this is A times X. Okay, so the way this matrix acts on a vector is basically by stretching it by a factor of 2, because you have 2. So this matrix is actually have a name, and sometimes you call this matrix dilation matrix. Why it's called dilation matrix? Because that's what is effect on a vector. It just stretches it by a factor of 2. Okay, so that's really the geometrically the matrices do something to vectors, and sometimes it's easy to understand them, and sometimes it's not. Let me take you another geometric example, but that's what I plan for the rest. So I'm going to take the following matrix A. Sorry. So example number 2, my matrix A is the following: 1, 0, and 0, minus 1. This is my A. And the T is from R2 to R2, takes a vector X to A times X. And our goal is, again, to geometrically understand, for this simple matrix, what it does geometrically. So I'm going to take A, I'm going to let it act on any vector and ask myself, what it's doing. So let me take T of X. Okay. T of X is what? So it means T of X1, X2. That's what I mean by T of X. And right here, but for the same reason in the previous problem, I drew a vector and its image on the same axis, on the same plane. I'm going to do that here because you can see exactly what's the image here. Okay, it's equal to what? What does T do? Takes the matrix A and multiply it by the vector. So this is my A. Okay, that's my matrix. And let's see, this give me what though? So this is going to be equal to row column x1 plus x2, x1, and 0 x1 minus x2. Okay, so what does this transformation do? So multiplying a vector by A from the left, it takes the vector x1, x2. It's going to take this vector to which vector? X1 and minus x2. This is x1 and minus x2, which is right here. So that's A of x. That's A of x1, x2. Okay, now we have to think about it. What does multiplying a vector by this matrix from the left does to a vector? So this is my x1, x2. So what do you think? I have an answer on chat. I see it, but I want better than that. So it takes x1, x2 to x1 minus x2. So what is actually doing to a vector? You can put it in a nice geometrical idea. What's the relationship between that and that? What's this with respect to this? It's mirroring it around the x-axis. It's reflecting it across the x1 axis. And remember here, this is the x1 and this is the x2. So if we're thinking about that, that's what it does. So what it does, it takes a vector basically, and it reflects it across the x1 axis. So what action is to reflect across the x1 axis. So this matrix also can have a name, and its name is what it does to a vector. So this matrix 1, 0, 0, minus 1, we actually give it a name, and we call it the reflection matrix because that's what it does. So that's the reflection matrix across the x1 axis. Okay, so left multiplying a vector by this matrix has definitely a geometrical impact. What it does is it just reflects it. So intuitively, if you have for example, if you have a square in here, square like this, and you take every vector in the square and you left multiply it by A, this transformation is actually going to take this square and reflect all of it down here. If you take any vector and reflect it, What the transformation will do is take the square and actually reflect it across the X1 axis. And you get this type of image. Okay, so that's really the effect of this matrix. All right, and those ideas actually are for those of you who are in computer science major, those ideas are used a lot in computer graphic, because usually that's what goes behind the scene when you have a picture and then it's reflected and so on and so forth. What actually happens is that your computer is left multiplying by the reflection matrix, and that's how they will get the outcome of reflecting across the X1 axis. So that's what goes in the background. All right, that's it for today. Please do your homework for Wednesday and come to class with questions. That's the only way we're gonna get through this course. All right, for those who have any questions, they can stay, the rest can leave. Thank you.